Hello and welcome to this online lecture for Math 200. We are going to be covering the last of the new material for your class this week. The following week you have, I think, maybe a project and a final exam review due, and then the last week is set aside for you to take your final. So I will be doing an exam review next week, but then we will not have a session the week of the final. So today we're going to be covering Chapter 12, which just walks through some additional inferential procedures. So we're going to start with Section 12.1, which is the goodness of fit test. So I want to go through some characteristics of the chi-square distribution first. First of all, it's not symmetric. Its shape depends on the degrees of freedom, just like students' t distribution. So if you remember when we did students' t distribution, the shape depended on the degrees of freedom. The same is true with chi-squared. As the number of degrees of freedom increases, it becomes more nearly symmetric. And the values of chi-squared are non-negative. That is, that the values of chi-squared are greater than or equal to 0. So here are some examples of chi-square distribution with various degrees of freedom. You can see as we have more and more degrees of freedom, we have something that starts to approach something that is symmetric, even though it's still a little bit skewed to the right. A goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So the first thing we need to talk about is expected counts. So let's suppose that there are n independent trials of an experiment with k greater than or equal to 3 mutually exclusive possible outcomes. We're going to let P1 represent the probability of observing the first outcome, and E1 represent the expected count of the first outcome. P2 is going to be the probability for the second outcome, and E2 is going to represent the expected count for the second outcome, and so on. So the expected counts for each of the possible outcomes are going to be given by EI is equal to mu of I, which is equal to n times probability for that particular outcome that you're talking about, all the way from I equals 1 up to k groups. So we're going to work with this example throughout this whole first section. So I'm going to read through this and then we're going to find some expected counts. So a sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is any different today than it was in the year 2000. According to the U.S. Census Bureau, in 2000, 22.8% of grandparents have been responsible for their grandchildren less than 1 year, 23.9% have been responsible for their grandchildren for 1 or 2 years, 17.6% for 3 or 4 years, 35.7% for 5 or more years. If the sociologist randomly selects 1,000 caregiving grandparents, we want to compute the expected number within each category, assuming that the distribution has not changed from the year 2000. So step 1 is to identify the probabilities, and we have them listed here. These were given in the setup of the problem. You want to change them so that they're decimals instead of percentages, so you move your decimal 2 places to the left. So for year 2000, this is the distribution that was given. Probability of less than 1 year was 0.228, and so on. So there are n equals 1,000 trials for our new experiment that we're trying to do. So in order to get the expected counts, all we have to do is take our n, which is 1,000, and multiply by that probability that we had from the previous example, or the previous survey. So we have 1,000 times 0.228, so we get 228. So it means that there are 228 expected grandparents out of the 1,000 who will have cared for their grandchildren for less than 1 year. 239 for 1 to 2 years, 176 for 3 to 4, and 357 for at least 5. We're going to come back to that example in a minute, but I want to go through a couple of other things first. And the first one of those is the test statistic for the goodness of fit tests. So we're going to let OI represent the observed counts for category I. EI is going to represent the expected counts for category I. K is going to represent the number of categories, N represents the number of independent trials, and so we have this formula here, chi-squared, that's what this symbol is right here. So chi-squared is equal to the sum of our observed counts minus our expected squared divided by our expected. And then once we calculate all of those, we just add them all up from I equals 1 all the way up to K. Now this is going to follow the chi-square distribution with k minus 1 degrees of freedom. There are a couple of things that have to be true. All expected frequencies have to be greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. It's important to note that you remember this formula here, that our expected counts are going to be n, which is our sample size, times our probabilities. So here's just a cautionary note. Goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. If you wish to compare 2 or more populations, you have to use the tests for homogeneity, which are presented in the next section. We'll get to those in a little bit. Okay, so the steps for the goodness of fit test. First of all, you need to determine a null and an alternative hypothesis. H0 is your null hypothesis. That's going to state that the random variable follows a certain distribution. The alternative hypothesis is going to be that the random variable does not follow the distribution in the null hypothesis. Then we decide on a level of significance alpha, depending on the seriousness of making a type 1 error. And in the problems that you'll be doing, this is typically given. Then we calculate the expected counts like we just did in the previous example. So we take our sample size, multiply by our probabilities. We verify that all requirements are met for the goodness of fit test. So we need all of our expected counts to be at least 1, and no more than 20% of them can be less than 5. Another cautionary note here, if the requirements in step 3b are not satisfied, one option would be to combine 2 or more of the low frequency categories into a single category. So if you have a couple that are pretty small and it makes sense to put them together, then that is an option for you. Okay, there is a classical approach and a p-value approach. I'm just going to cover the p-value approach in this section, but if you want to look at the classical approach, or if you want to see how to do some of this using technology, I would reference your textbook. So you compute the test statistic. It was given on a previous slide, but our chi-squared test statistic is going to be equal to our observed minus our expected squared divided by our expected. Once we have that for each thing, or each group, you add them all up. And then using table 7, we obtain an approximate p-value by determining the area under the chi-square distribution. We look for k minus 1 degrees of freedom. And we're looking to the right of the test statistic. So if you see this graphic here, we have our chi-squared test statistic that we obtained using the formula on the previous page, and then our p-value is the area under this to the right. If our p-value is less than alpha, just like we have a typical kind of way of either rejecting or failing to reject, it's the same thing for this. If p-value is less than alpha, then we reject H0, and we state a conclusion. So we have the same problem here. A sociologist wishes to determine whether the distribution for number of years caregiving grandparents are responsible is any different than today than it was in the year 2000. So we have these same numbers that are given here. We already collected these frequencies. Okay, these are our expected frequencies for our 1000 for our new survey, and we want to test the claim that the distribution is any different today than it was in the year 2000. Alpha equals 0.05 in this case. So step 1, we want to know if the distribution today is any different than it was in 2000. So the way that we write the hypotheses are our H0 is that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is the same today as it was in 2000. And our alternative hypothesis is that the distribution is different today than it was in the year 2000. So null hypothesis is that it's the same. Alternative is that it's different. Our level of significance was given, alpha equals 0.05, and the expected counts have been recorded right here. We also have some observed counts from the actual survey. Okay, so this would be your 1,000 people that were actually asked, and this is what we would expect based on the assumption that it follows the same distribution as the year 2000. Since all of the expected counts are at least 5, we don't have any issues there, so the requirements for the goodness of fit test have been satisfied. So we calculate our test statistic by taking our 252, that's our observed, minus our 228, squaring that, and then dividing by 228. And then we go to the next group, 255 minus 239 squared over 239. And you keep going, you add each of these up. Make sure you're really careful when you're putting these in your calculator. Make sure you have parentheses around your numerators. And you should get 6.605 when you go ahead and plug all of that in. Now there are k equals 4 categories, so we have 3 degrees of freedom. So we want to look on our table. The p-value is the area under the chi-square distribution with 3 degrees of freedom to the right of chi-squared is equal to 6.605. And you can do this using your calculator or the table. Your calculator will give you a more exact value. It's a little easier as well. And we get a p-value around 0.09. Now, since our p-value is greater than the level of significance, our alpha, we fail to reject h0. So we would say that there is insufficient evidence to conclude that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. So there's not sufficient evidence to conclude that it's any different than it was in the year 2000 at the alpha equals 0.05 level of significance. Okay. Section 2.2, we're going to do some tests for independence and talk about the homogeneity of proportions. So objective 1 is to perform a test for independence. Again, we have a chi-squared test. This one's the test for independence. It's used to determine whether there is an association between a row variable and a column variable in a contingency table constructed from sample data. The null hypothesis is going to be that the variables are not associated, so independent, okay? But the alternative hypothesis is going to be that the variables are associated or dependent. So in other words, H0, variables are independent, H1, variables are not independent. The whole idea behind this testing is to test the types of claims to compare actual counts to the counts that we would expect if our null hypothesis were true. So if the values were actually independent. And then if a significant difference exists between the actual and the expected, then we take this as evidence against our null hypothesis. Now, it's important to remember that if two events are independent, the probability of E and F happening is just the product of the two, probability of E times probability of F. That's our multiplication principle for independent events. And we can use it to obtain expected proportion of observations within each cell under the assumption of independence and multiply this result by n, the sample size, in order to obtain the expected count within each. So I'm going to walk through one example that does this. We're going to see this example a little later. And then there is an additional formula that you can use instead of this one. Either way, it doesn't really matter. You will end up with slightly different answers based on rounding, but that's not a big deal. In a poll, 883 males and 893 females were asked, if you could have only one of the following, which would you pick? Money, wealth, or love? The responses are presented in the table below. Determine the expected counts within each cell, assuming that gender and response are independent. So, for example, we had 82 men who answered that money would be what they choose. We had 574 women answer that health would be what they choose. So first we just create some column totals and some row totals. This should be pretty easy. You just add these up to get the 883, add these up to get the 128, and so on for a total of 1,776. And then you compute all of the relative marginal frequencies for the row and the column variables. And what we mean by that is we take our 883, that was the sum of these three, so that was our row total, and divide by our total, which was 1,776. So we get 0.4972 for this one, 0.5028. For this one, we take the sum of 82 and 46, which is 128, divided by our table total, 1,776, and we get 0.0721, and so on. And the sum of these, the sum of the column should be 1, the sum of this row should also be 1. That's a good thing to check. So assuming gender and response are independent, we use the multiplication rule for independent events to compute the proportion of observations we would expect in each cell, and we get the following. So then we multiply the expected proportions from step 3 by 1776, which is our sample size, in order to obtain the expected counts under the assumption of independence. So we take our 1776 and we multiply by our 0.0358 to get the 63.5808. And the 0.0358 is obtained by taking the 0.0721 and multiplying it by the 0.4972. For this one down here, we would take our 0.0721, so that's this column, and multiply by this row, the 0.5028. And so we end up with all of these expected frequencies here. Another way of doing this, which is slightly easier, is to just take your row total, multiply by your column total, and then divide by the table total. That will work as well. Okay, so the test statistic for the test of independence, we're going to let OI represent the observed number of counts in the ith cell, and EI represent the expected number of counts in the ith cell. So this is the same idea as the last section. Our chi-squared statistic is just obtained by taking the sum of our OI minus EI squared and dividing by EI. This approximately follows a chi-squared distribution, except the degrees of freedom are a little bit different than the last one. So for this one, we take the number of rows minus 1, we take the number of columns minus 1, and then we multiply by those two numbers by one another in order to get the number of degrees of freedom. This is all provided that the expected frequencies are greater than or equal to 1 and no more than 20% are less than 5. So the chi-squared test for independence, in order to test association or independence of two variables in some contingency table, you'll use the following steps. First thing is to determine the null and the alternative hypotheses, and these should be pretty easy. Null hypothesis is that the row and the column variable are independent. Alternative hypothesis is that the row and the column variable are dependent. Step 2 would be to go ahead and choose a level of significance, which is alpha, depending on the seriousness of making a type 1 error. This is normally given in the problem. Step 3 would be to calculate the expected frequencies for each of the cells, verify that the requirements are met, and then compute the test statistic, and use your table to determine the approximate p-value by determining the area under the chi-squared distribution with r-1 times c-1 degrees of freedom, where r is the number of rows, c is the number of columns. Again, you can also use a calculator for this. If your p-value is less than alpha, then you reject h0, and then you state a nice conclusion. So let's go back to the same question where we had the males and the females pick money, health, or love. We have these results down here. So step 1 would be to go ahead and identify the null and the alternative hypotheses. The null hypothesis is going to be that gender and response are independent, whereas the alternative hypothesis is that gender and response are dependent. The level of significance in this problem is going to be 0.05. And the expected frequencies we already computed in the previous example. And they're given in parentheses below, along with the observed frequencies above. So we would expect 63.5808, but there were actually 82 responses for men who responded with money. So since none of the expected frequencies are less than 5, the requirements have already been met. So we just calculate our test statistic by just taking our 82, that's what we actually got, minus our 63.5808 and squaring that, and then dividing by the 63.5808, and we do that all the way across, and we end up with 36.82. Now we know that there are 2 rows and 3 columns, so in order to find the number of degrees of freedom, we take 2 minus 1, which is just 1, and multiply it by 3 minus 1, which is just 2. So we have 1 times 2, which gives us 2 degrees of freedom. Now the p-value is the area under the chi-squared distribution with 2 degrees of freedom. To the right of our chi-squared is equal to 36.82, and that's approximately 0. So since our p-value is less than the level of significance, we do reject the null hypothesis at the alpha equals 0.05 level. So we would say that there is sufficient evidence to conclude that gender and response are dependent at the alpha equals 0.05 level of significance. So to see the relation between response and gender, we can draw bar charts or bar graphs of the conditional distributions of response by gender. So you need to remember that a conditional distribution lists the relative frequency of each category of a variable given a specific value of the other variable in a contingency table. So if you look at the values for men, we have 82, 446, 355. So we just calculate the proportion that's in each of those. So we end up with 0.09, so about 10% of men answered with money. About 51% answered with health, and about 40% answered with love. We do the same thing for women. About 5% of women answered money, 64% answered health, and 31% answered love. And so if we put these bar charts right by one another, we can kind of see where the differences might lie. It looks like the largest difference is between the males and the females in terms of who answers health. Okay, there are a lot more women who answer health than men. Okay, objective 2 is to perform a test of homogeneity of proportions. So in a chi-square test for homogeneity proportions, we test whether different populations have the same proportion of individuals with some characteristic. So the procedures for performing a test of homogeneity are just identical to those for the test for independence, which is very nice. So let's look at this example here. The following question was asked of a random sample of individuals in 1992, 2002, and 2008. It says, would you tell me if you feel being a teacher is an occupation of very great prestige? The results of the survey are presented below. So, for example, in 1992, 418 answered yes, 602 answered no, and then the results are given for 2002 and 2008 as well. We want to test the claim that the proportion of individuals that feel being a teacher is an occupation of very great prestige is the same for each of the years. So the null hypothesis is a statement of no difference, okay? So we would say that the proportions for each year, the proportions of people who feel that being a teacher is an occupation of very great prestige is going to be equal for each of them. So we would say that P1 equals P2 is equal to P3. And our alternative hypothesis is that at least one of these proportions is different from the others. The level of significance is going to be 0.01. So the expected frequencies are found by multiplying the appropriate row and column totals and then dividing by the sample size. So these are given in parentheses in the table below along with the observed frequencies. So this is something we've already done for a similar problem, so I'm not going to redo that. But these are kind of what we would expect, and above it is what we actually observed. None of the expected frequencies are less than 5, so all of our requirements have been satisfied. We go ahead and compute our test statistic by taking 418 minus 475.554. So we take what we actually observed minus what we would expect, square that, divided by what we would expect, same as all other chi-squareds, and then we add them all up, and we should get 24.74. Now there are 2 rows and 3 columns, so we find the p-value by using 2 minus 1 times 3 minus 1 degrees of freedom. This is the same as the last example actually. So we get 2 degrees of freedom. The p-value is going to be the area under the chi-square distribution with 2 degrees of freedom to the right of 24.74. And again, this is approximately equal to 0 just like the last one is. 24.74 is a fairly large number. So because our p-value is less than alpha, we do reject the null hypothesis. So we can say that there is sufficient evidence to reject the null hypothesis at the alpha equals 0.01 level of significance. So we can conclude that the proportion of individuals who believe that teaching is a very prestigious career is different for at least one of the 3 years, meaning that it hasn't stayed static over the course of the 3 years that we're talking about. Okay, section 12.3 is all about testing the significance of the least squares regression model. Now, it's important that you have access to either Minitab, a graphing calculator, or some other statistical tool when you're doing your homework, because there is a question that requires that. The least squares regression model is going to be given by the following equation, and this should be review. yi equals beta 1 xi plus beta naught plus our error. Okay, yi is going to be the value of the response variable for the ith individual. B0 and B1 are the parameters that are going to be estimated based on sample data. They're written as betas here because they're not samples yet. Xi is the value of the explanatory variable. EI is the random error term, has a mean of 0 and a variance of sigma squared of EI, which is just equal to sigma squared. The error terms are going to be independent. I is equal to 1 all the way to n, where n is our sample size, or the number of ordered pairs in the data set. So the first objective we want to go through is computing the standard error of the estimate Now, this is something that I would definitely do using some kind of statistical tool. But we do have this formula here. The standard error of the estimate, or SE, is found using the following formula. So we take the sum of the squared residuals, which is going to be yi minus yi hat, square that, add it all up, and then we divide by n minus 2, and then we take square root. That gives us our standard error for our estimate. So let's look at an example. We're going to use this drilling data. We've used this in previous sections as well. But this shows the depth at which drilling begins and then how long it takes to drill 5 feet in minutes. So as you drill deeper and deeper, it takes longer and longer to drill 5 feet. So using technology, we find the least squares regression line to be the following. Y hat equals 0.0116x plus 5.5273. And you can do this using Excel, Minitab, your graphing calculator, really anything. Steps 2 and 3. The predicted values as well as the residuals for the 12 observations are given on the table in the next slide. So if we look at these, we have our x's, we have our y's, we have our y hats, which were given by basically plugging our x into our regression equation. We take our y minus our y hat and we square it, and then we add them all up. That gives us the sum of the squared residuals, and we get 2.7012. And then what we do with that is to find the standard error, we take our sum of our squared residuals, which was 2.7012, divided by n minus 2, which in our case we had 12 observations, so we do 12 minus 2, which gives us 10. Divide those, take square root, and we get 0.5197. And again, this can be done using a statistical tool. We want to also make sure that we know how to verify that the residuals are normally distributed. So if we look at this probability plot of our residuals, this is for our same data. It has our 12 observations here. We don't have anything outside of these blue bands, so this looks pretty good. Next thing we want to do is conduct some inference on the slope. So we're going to do a hypothesis test regarding the slope coefficient beta 1. So to test whether two quantitative variables are linearly related, we use the following steps, provided that number 1, the sample is obtained using random sampling, and number 2, the residuals are normally distributed with constant error variance. So step 1 is to determine the null and the alternative hypotheses. They can be structured one of 3 ways, just like a lot of the hypothesis testing that we've done. A two-tailed test would be beta 1 equals 0, against beta 1 not equal to 0. We have left-tailed, which is less than, right-tailed, which is greater than. We select a level of significance depending on what type of type 1 error we want to deal with. Compute our test statistic. T naught is given by B1 minus beta 1 over the standard error for B1. And that's just going to be B1 over SB1. This follows the student's T distribution with n minus 2 degrees of freedom. And we use table 6 in order to approximate the p-value. So p-value approach, you're used to seeing all of this. You should know what a left-tailed, right-tailed, and two-tailed tests look like at this point. If p-value is less than alpha, we reject, and we state a conclusion. So it says, caution, before testing H naught that B1 equal or beta 1 equals 0, be sure to draw a residual plot to verify that a linear model is appropriate. So let's test the claim that there is a linear relation between drill depth and drill time at the alpha equals 0.05 level of significance using that same drilling data that we did before. So first thing we want to do is verify the requirements. We assume that the experiment was randomized so that the data can be assumed to represent a random sample. We already confirmed that the residuals were normally distributed by constructing and looking at a normal probability plot. And then to verify the requirement of constant error variance, we plot the residuals against our explanatory variable, which is our drill depth. And if we look at this here, there is not a discernible pattern, so this looks fine. Really on this plot, the residual plot, you're looking for any kind of strange patterns that you might see, maybe like a cone shape that's going out or something like that. So step 1 is we want to determine whether a linear relation exists between the drill depth and the drill time. So we're going to use a two-tailed test. We're going to set our null hypothesis up as beta 1 equals 0 versus our alternative, since it's a two-tailed test, as beta 1 not equal to 0. We have an alpha equals 0.05 level of significance. And then using technology, we obtain an estimate of beta 1 as B1, which is going to be 0.0116. And now we want to compute the standard deviation of B1. So the calculations for that are on the next slide. So in order to do that, we take our xi minus our x bar, we subtract it all the way down, we square that, and then we add everything up. We get 30,006.25. And then we take our standard error, which we had already calculated, the 0.5197 that was calculated a few slides back, and divide by the square root of 30,006.25, and we get 0.003. So this gives us SB1. So our test statistic is going to be found by taking B1, which is 0.0116, and dividing by 0.003, which gives us 3.867. That's our test statistic. So since this is a two-tailed test, the p-value is going to be the sum of the area under the t-distribution with 10 degrees of freedom to the left of negative 3.876 and to the right of positive 867. So using table 6, we find that 10 degrees of freedom, the value for 3.867 is somewhere between 3.581 and 4.144. Those are the values you actually see on your table. And those correspond to probabilities between 0.0025 and 0.001. So in order to get our actual p-value, we need to multiply by 2 since we have a two-tailed test. So we have values between 0.002 and 0.005. So since our p-value is going to be less than 0.05, it's quite a bit less than that, we do reject H0. So we'd say that there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that a linear relation does exist between drill depth and drill time. Okay, objective 5 in this section is to construct a confidence interval about the slope of the least squares regression model. So a 1 minus alpha 100% confidence interval for the slope is given as follows. So you take V1 and you add and subtract your critical value, T alpha over 2. You multiply that by SE divided by the square root of the sum of xi minus x bar squared. And here, T alpha over 2 is computed using n minus 2 degrees of freedom. So an important note, the confidence interval formula for beta 1 can be computed only if the data are randomly obtained, the residuals are normally distributed, and there is a constant error variance. So we have those same assumptions that we have to work with. So let's do an example here. Let's construct a 95% confidence interval for the slope of the least squares regression line for the drilling example. So requirements have already been met. We already talked about that. We also determined that B1 equals 0.0116 and that SB1 is 0.0030. So we're going to use those numbers again. T 0.025, that's T alpha over 2, is 2.228 for 10 degrees of freedom. So for our formulas, we take our lower bound, which is our B1, which is 0.0116, and we add and subtract our critical value multiplied by 0.003, and we get 0.0049 and 0.0183. So just like we interpret other confidence intervals, we're going to start it the same way. We are 95% confident that the mean increase in the time it takes to drill 5 feet for each additional foot of depth at which the drilling begins is between 0.005 and 0.018 minutes. So that means as you drill deeper, it's going to take longer in order to drill those same 5 feet. Okay, lastly is section 12.4, which goes through some confidence and prediction intervals. So confidence intervals for a mean response are intervals that are constructed around a predicted value of y at some given level of x. They're used to measure the accuracy of the mean response of all individuals in the population. Now, prediction intervals are slightly different. They're constructed around the predicted value of y, and they're used to measure the accuracy of a single individual's predicted value. So that's for one value, whereas the confidence interval for a mean response is for the mean. So let's do the confidence interval for the mean response first. We have these formulas here. These are given on your formula sheet, so there's no need to memorize this. We have y hat plus and minus our critical value, which is T alpha over 2 times SE multiplied by the square root of 1 over n plus x star. Now x star is the given value of the explanatory variable minus x bar squared divided by the sum of xi minus x bar squared. N is the number of observations. T alpha over 2 is the critical value. Again, we have n minus 2 degrees of freedom. So let's construct a 95% confidence interval around the predicted mean time to drill 5 feet for all drillings started at a depth of, we're going to do 110 feet. Now we could do this for anything, but we're doing it for 110. So we know our least squares regression line was calculated as follows. Y hat equals 0.0116x plus 5.5273. We already had found that. The predicted mean time to drill 5 feet for all drillings that start at 110 feet is going to be found by taking 110 and plugging it in for x. And if you do that, you get y hat equals 6.8033. It's important to recall all of these values because we're going to be using them again. And all you really have to do is just plug in very, very carefully. So we have 6.8033 plus and minus for our lower bound and our upper bound, 2.228 times 0.5197 multiplied by the square root of 1 over 12, that's 1 over n, plus 110 minus 126.25 squared over 30,006.25. And you have to do this very, very carefully in your calculator. You end up with a lower bound of 6.45 and an upper bound of 7.15. So what we would say is that we are 95% confident that the mean time to drill 5 feet for all drillings starting at a depth of 110 feet is going to be somewhere between 6.45 and 7.15 minutes. So that would be the average. Now we're going to do it for an individual response. So this is a prediction interval. So we have kind of a similar sort of equation here for our lower and our upper bounds. We're going to just plug and chug in here. We already have all of these values. This time we want to construct a 95% confidence interval about the predicted time to drill 5 feet for a single drilling, starting at a depth of 110 feet. And again, we have our regression equation. We plug in 110 for our x, and we get 6.8033. And we can recall all of these same facts. We plug everything in, and we get 5.59 to 8.01. You'll notice this is a little bit wider than the previous interval, because what we're talking about now is we still want 95% confidence, but we want it for just one particular value instead of for the average. We know that we're going to have kind of extreme low and high values occasionally when we're just looking at single values, but when we look at the mean over time, it should be more centralized because we're taking the average. So for the mean, we end up with a smaller interval. For the prediction interval, for one value, we end up with a larger interval. So it's from 5.59 to 8.01. So if we want to interpret that, we just say that we are 95% confident that the time to drill 5 feet for a random drilling starting at a depth of 110 feet is somewhere between 5.59 and 8.01 minutes. All right, so that is it for this lecture.